called as shortly is called SALC method. So this is called as symmetry adapter linear combinations. So this is symmetry adapter. So what we did was we just choose the point group. It could be group or subgroup. And from that we got reducible representation. And then we did by reduction method, IRs of symmetries we got. So once we get the IRs, then we did the projection of orbitals. Remember, we took the 3 orbitals, right? 1, 2, 3. So we took 3 orbitals and then projection of orbitals with respect to IR, this IR. And then we did linear, we took linear combinations. Just say, it's called as symmetry adapter linear combination. So we have to make sure the symmetry matches. It's called as symmetry adapter linear combinations. And then in the process we normalized it. So let's say normalized it. I call normalized files. Then we used Huckel's method, right? Huckel's file. Huckel's approximation, you can say. Pi orbital approximation. And then we got 3 orbitals. If you remember, alpha. And the other one was alpha plus or alpha minus 2 beta. Okay, alpha plus 2 beta. And then alpha minus 2 beta. So one was bonding orbital, other is non-bonding, and third one is anti-bond. You get something like this. This is of one symmetry and other 2 were of other symmetry. Right? This is what we did last class. So this is A2 and B1. This is A2 symmetry and this is B1 symmetry. So the entire process I just summarized in a few steps. We start with the group and then reducible representation we wrote for orbitals. IR we found out, projection out the orbital with respect to those IRs. Then we applied the symmetry adapter linear combinations. You remember we summed up 2 numbers and then 2 functions and then we subtracted 2. And whatever remaining we got, we normalized it. We labeled it as files. And then we applied a Huckel's pi orbital method. If they are nearest the same type of orbitals, if it is nearest, then it's alpha. If it is of different type, it is beta. And then we got the energy levels. So these are the energy we got. So these are okay, its corresponding symmetries are given. So maybe I didn't tell about subgroup. So what is a subgroup? Any idea? What is subgroup? Okay, in a group, say, I think a few class before we studied what is called as a group, the set of elements which satisfies four rules, right? Four rules like associative, like that. The identity should exist, inverse exist. So there are four properties to define a group. In a group, there could be a smaller set of elements which obey these four properties. So that is called as a subgroup. So subgroup is a set of elements present in a group. They are smaller in number, but they also satisfy the four rules of a group. So that is called subgroup. So I'll give an example. You will appreciate it better. So let's take example of D. You can say D2H. So if you write, there are C2. You have a series of things, right? Sigma H. Whatnot. You have series of things. And then you can say X, C2Y, C2Z, I, sigma XY, sigma YZ, sigma ZX. So like this, you have many. So these are the things present in D2H, and that could be more. Like if instead of D2H, you can have a subgroup. Say, for example, D2. Only if you take the D2H subgroup is D2. That could be multiple. Like when D2 group is E, and then C2X, C2Y, C2Z. So this is D2, and there could be more. Like C2H, it could be. So if you write C2H, E, C2, I, and sigma. Sigma, all sigma. So I take, and then H, particularly sigma H. Out of these three sigmas, the one is sigma H. Okay, and then that could be C2V also. E, C2V, you know, right? So C2 sigma V prime and sigma V double prime. See, that could be two sigma V's. That's what's written here. You can say it's XZ and YZ. And C2. C2 is E and C2. And simplest one is C1. So this is just E and C1. So these are various subgroups. So all these C2H is a main point group or it's a group, but these are all called as subgroups. Subgroups of D2H. Okay, so subgroup means the properties of groups are all or obeyed by certain elements which are part of the bigger group. So D2H is a group, and these are all subgroups. So in our method in finding out the symmetry of orbitals, we really don't have to take the full group. We can simply construct the subgroup and then find out the symmetry. So that is much easier. So I just give an example. I won't do everything. You just work it out. Okay. So I just give an example of 1,3-butadiene. Okay. So I just take 1,3-butadiene. Cyclobutadiene.
Sir, hello, sir.
Yeah.
Could you please repeat a subgroup again?
Let me just sum this. Yeah, yeah. Somebody was asking something. Yes, please. Yeah, somebody was asking something. Okay, if not, the example is say 1,3 cyclopyridine is a D4 as such point group is D4H. Okay, but for our derivation or for our study of finding out the symmetry of orbitals, one can use instead of D4H, we can use just subgroup D4 subgroup. That's what I'm saying. So instead of using a full group, one can use a subgroup for getting the symmetries. Then we can get the so on. So this is a 1,3 cyclopyridine. You have 4 orbitals, so you can build as 5,1, 5,2, 5,3, and 5,4, all equivalent. And then we can write the reducible basis set for a D4 one group. After writing the reducible basis set, you find out the irreducible representation. After writing the irreducible representation for all these orbitals, you perform a projection operator, projection method with respect to IRs present. Once you get the projection, then you get the 4 wave functions, because 5,1, 5,2, 5,3, 5,4 are there. You get 4 wave functions. Once you have the 4 wave functions, you can you can take the what? You can take the linear combinations. So you add 2 and then subtract 2, and then you get capital Phi's, and then you normalize it. After normalization, use the Huckel's method to get the energy ordering. So I give the answer. So you will have 4 orbitals, right? So you get 4 alpha, 4 energy levels. In that, 2 will be, I guess, 2 will be degenerate, and then other 2 you just find out. So this is one is.
Sir, excuse me, sir.
Yeah, tell me.
Sir, here the D4H point group, it will have a number of subgroups, right? But in this case, for the finding of to find the symmetry of orbitals, you are saying that we should use the subgroup D4.
No,
So can we use other subgroups?
We can use. It's not that
and they will.
we
Okay,
can.
and they will get the same results. Hello.
Yeah, go ahead.
Sir, they will give the same results if we used the other subgroups with planes and that I also.
Yes, you will get the same result. I can tell you. If you use subgroup D4, you get these 4 orbitals as energies, and you can say these are all degenerate. So E function will be there, and these 2 are different. I'll just give that. So it is this will be in the form of E symmetry, and then this will be one will be A2, other one A2. I just say it's one is A2. Okay, other one will be I think B1, B2. So if you use D4, okay, so you get these are the IRs. So one is E, which are degenerate. That's why alpha you're getting. Another 2 is one will be of A2 type, other will be of B2. But this can be extended to D4H. So after derivation, if you extend this D4H, if you see the character table, A2 is nothing but it will be A2U. Okay, and E will be transforming to EG. And then B2 will be either one. I mean, it could be B2U or B2G. Most probably in this case B2G only, because we're taking the ground state pi orbital. So if you use just subgroup, your derivation is simpler, and you get the energies with appropriate symmetries. Degenerate are E, and then this will be lowest. B2 will be the lowest because this beta is in negative. So this will bring down. So B2 is negative, and then A2 will be above. So if you see the energy ordering, you will find alpha here, 2 alphas. This is alpha, this is also alpha, and this will be alpha minus 2 beta, and this will be alpha plus 2 beta. So you end up with something like this. And what I'm saying is, so this will be A2 symmetry. This is B2 symmetry. This is A2 symmetry, and this will be E symmetry. If you take a subgroup as your starting representation, once you extend it, it ends up with this will be A2U, and then E will be EG, and B2 will be, it could be either one, B2U or B2G. This is just to simplify our long derivation. Okay, so instead of taking a full group, one can take a subgroup, and subgroup is basically subgroup is also elements present, a smaller number of elements present in a group which obey all the properties of a group. Okay, so you can see here the H will be lower. So H will be just 4 here. Yeah, so here it's 4H. Right, H it's 4, and then here it's also 4, 4, 2, 2. The order of the group will be different, okay, in subgroups. And whereas in this case it is 8. In D2H it was 8, whereas in other things it is slower. Okay, so I give an assignment. You take your time, maybe 1 week, to find out find pi orbital symmetries. Symmetries of 1,3-cyclobutadiene. If you start with D4H, I have no problem. Go ahead. You will end up with these answers. I've given the answer. These are the energy ordering. If you use the subgroup, then you have to just use a D4 point group and then go ahead. Okay. You agree?
Sir, excuse me, sir.
Yes.
Sir, if we are only asked to find the pi orbital symmetries, we can do this thing in qualitative way also, right? By
Yes.
applying the symmetry operations over the orbitals.
Yes. So
For symmetries only, for pi orbital symmetries only.
pi orbital symmetry.
So by applying the.
So basically, it is.
So by applying only the operations.
Maybe I have to reframe the question. You have to find out the pi orbital symmetries of
this method is suitable for finding the energies and symmetries.
Yeah, can you please repeat energies?
Sure. The energies and symmetries, because we can find the symmetries in qualitative way also, but by that we can't find the energies.
Yes.
Like in the Huckel-Amity that we do the quantum.
Yes, we cannot find the energies by
Then also.
pi orbital symmetries using Huckel's method. So when you use this method, you will get the energy also. For each energy, what is the symmetry, you will get it. Like this energies, you will get it. Okay, that's the logic. And same thing, one can do it for benzene also. Benzene, if you start T6H, right? So you get 6 orbitals. When you take 6 orbitals, then you will get 6 energy levels in benzene. And then you can find out what are the symmetries of these 6 energy levels. And they are not, some of the orbitals will be degenerate in benzene also. So you will have maybe 2 orbitals or doubly degenerate, and remaining 2 will be separate. So one can find the energies also, and also its corresponding symmetries if you use this method. So this method is called as Huckel's pi orbital method, adapting SALC method, symmetry adapted linear combination method. Okay, so this is one way. We will see maybe in future class, maybe 1 or 2 class later, we'll see how we use the variational method to get the energies also. Okay, so we never use the variational energy, but same equation we'll arrive at. These are energies, right? The same thing we arrive at by using a secular determinant. and then get the energy. So we are going to compare that. Okay, there are two methods to arriving it, but here you will get the symmetries also. So group theory tells the by all this procedure, it tells which orbital symmetry will be there for the corresponding energy. Okay, I suggest you read it. Okay.
And sir, for the assignment, we have to do only the cyclobutadiene or benzene also.
No, benzene, don't worry. But read it, read benzene, the exam.
Okay. Okay, sir. Okay,
Yeah.
sir.
Benzene now it takes very long time. 6 orbitals, right? So it's a very lengthy procedure. So very difficult. So we generally give the orbitals energy level and then ask to find out the delocalization energy in benzene. Okay, so basically we find the orbital energy, right? So once we know this, then we subtract with the pi, say ethylene molecule energy. So if you find the energy of benzene, H6, I would say pi, okay, minus energy of pi of ethylene. Ethylene is C2, H4. So I subtract with 3 times. So then I get delocalization energy. So something like this we can find out. So you find out the energy of benzene molecule, pi orbitals, and then we also can find out the ethylene molecule. Just ethylene is just this 2 orbitals, right? So you just get it. It's very simple. We can get it. There is a value given also, certain kcalories per mole. So that is given. So you multiply by 3 times, and then benzene energy you will get it. You subtract it. Whatever the difference is, delocalization energy. So it will be negative. So like this, we just give the calculation. Okay. And not only benzene, you can find out any molecule, pi system, aromatic system, delocalization energy. So I'll give the equation one more time when we study the variational approach and then get the delocalization energy. But time being, you work out the 1,3-cyclobutadiene. Fine, so far good. So the quiz paper, I'm evaluating it. Okay, I think by Wednesday I'll finish it. Okay, I can give the marks by that day. I can return it also by the time. Half of them have done it, but I think I'll be finishing it by the time. So next topic is MO theory of octahedral system. So say consider M L6 n minus, you can say n minus. Okay, so so we are going to study the octahedral system, metal ligand complexes. Yeah, with all the background, like we started with 1 month back, right? Almost or more than 1 month back, we started with point group, then capture table, and then what we got. I mean, we have seen the classes, and then matrices. Then we came to capture table. Then recently we just started talking about the orbitals, right? The pi orbitals. So with all the background, we're going to study the molecular orbital theory or MO theory of octahedral system. The same is applied for the square planar or tetrahedral, like that. Okay, so I just cover the only octahedral. Okay, so let's take an octahedral complex. So you have a system. You have a central atom, right? There is a metal atom central, and then there are connected by various ligands. So it goes from this also. So this is metal, central metal ion, and then these are various ligands. We can consider 6 ligands are there. Let's take the direction. This has x-axis, y-axis, and you can say this is the z-axis. Okay, considering it's a 3-dimensional representation. And then you have metal orbitals and ligand orbitals, right? So metal orbitals. So basically, logic is idea is metal orbitals have certain symmetry, and ligand orbitals have some symmetry. The symmetry should overlap to form the bonds. Okay. If there is no symmetry overlap, then they don't bind. And if some orbitals are not having the appropriate symmetry, like metal orbitals have multiple orbitals, they may not have corresponding orbitals in ligands. So it won't bind with the ligand. I mean, they just remain unbinded or non-binding. So that's method is called as. I mean, we apply the method called as symmetry adapted group orbitals. So we just consider into 2 parts, separate the problem in 2 parts. Central metal atom or ion, you can say. And then next is ligand orbitals. So ligand orbitals are combined with the metal by a method called as symmetry adapted GO orbitals. So symmetry adapted group orbitals. Okay. Okay, symmetry adapted. This thing symmetry adapted. The full form is SAGO method, or called as symmetry adapted group orbitals of ligands. Okay, so now let's start the labeling. Is it time to label? Yes. So we have so many ligands. So metal. I just call ligands. We are showing it is having sigma orbitals and also pi orbitals. They are forming a bond with metal, right? So I just call this one as sigma 1, sigma 2, sigma 3, sigma 4. We can say sigma 5 and sigma 6. So this is various ligands. Sigma orbitals are pointed towards a central metal atom or ion, and there are pi orbitals also of ligand. And say for this one, you can have 2 in or out, let's say. So I call it as pi 1, and this is pi 1 prime. There are 2 types. One is one type, other is other type. So p orbitals are all present. So this is pi, and then again similarly you can find 2 more. This is pi 2, 1 is prime, and again I can say pi 3 prime. This is pi 4 prime. You can say prime here, pi 4, and then here it is again. There are 2 more. 2 more is you can say in x direction or y direction. Pi 5 and pi 5. Again here it is 2 more. So like this, sigma and pi orbitals are present in ligands. Okay, so let me write. No, I'm not going to write a full group point group data table of OH. I simply write the essential part. Okay, you can refer always with the book or online this one. So I'm not writing full, but I just write only essential part. for OH, you have A1G. There are multiple things. I just leave it. And then EG is there. T1G will be there. T2G will be there. T1U, T2U. So I'm not writing the characters or corresponding this one. So I just call this one as A1G. A1G doesn't have anything here. There are some blanks. For EG, EG this x square, y square, into z square minus x square minus y square. You will find, I think, the character table of octahedral complex. You will find something like this for T1G. It is Rx, Ry, and Rz. Okay, so it's rotational vectors, rotational base is given. And for T2G, 3. So it's xy, xy, xz, and yz. All d orbitals kind of, right? And T1 you have here. So it is Tx, Ty, Tz. And T2u, again there is a blank. Okay, so you will find, I think you just Google it, you will find the character table of OH, and these are various symmetry elements you find there. I'm not writing it, so this is more relevant part. Now let's go back to the central metal ion or atom. So if you write the reducible representation for this central metal atom, it's a spherical, right? So you don't take this one. So it can be a combination of all these things. So central metal atom, you can say reducible or IRs. It's all possibilities are T1U plus, it's a direct product. So T1U, this one. So because XYZ vectors are present, so central atom can have T1U. Then A1G is very simple. A1G, since it's spherical, no? A1G has to be there. Okay. So A1G always will be there because spherical in shape. So the reducible representation will have A1G of metal, and then T2G. T2G you can see XY, YZ, ZX. So we just say ZX. So T2G will be there. And then last one is what? EG. Because EG you can say X square minus Y square, and then other things are there. Plus EG also will be there. Okay, so A1G is for spherical orbital, so it is A1G. So T1U is, T1 corresponds to XYZ. So it corresponds to basically PX, PY, PZ. So this is S orbital, you can say, of metal, and this corresponds to you can say PX, PY, PZ. Although highly, I mean, these orbitals may be inside your d orbitals, but still metal orbital also has S symmetry and also P symmetry. So P is PX, PY, PZ, that corresponds to T1U. Okay, so because it is coming from here, T1U, so XYZ is present. T2G, if you see, T2G is XY, YZ, and ZX. So T2U is basically D, XY, D, YZ, and DZX. Okay, so these three orbitals have T2G symmetry in metal, and EG is here. So it corresponds to, as you know, it's a D X square minus Y square. But group theory predicts it's a combination of all these things. But our chemistry says it is just DZ square. Yeah. So from the picture we know it's a DZ square. But anyway, group theory says it's a combination of. It's a combination of these three things. So DZ square and dx square minus y square form EG symmetry, and T2G forms dx dy dxy, dyz, dzx symmetry. And then a T1u of metal has, I mean, the px, qi, pz orbital of metal has T1u symmetry, and the metal s orbitals have A1g symmetry. So this is what we get for metal. The possible combination we have written, and then now we write. So I need a larger board, but I'm going to erase it. Is it okay? Now metal, we have just assigned this. Next step is for ligands. These ligands, there are 6 ligands. Similarly, we write for ligands the combinations, and then we match it with the metal. Which orbital will overlap with metal orbital? Okay, so that's the idea. So we are going to see which how it will overlap. So okay, so I just erase this. I hope you have noted down. If not, you just see in the Catter table of octaedral complex, octaedral point group, and you'll find these things. Okay, so we may keep using this table. I'm erasing it because I have to write for. I need this structure, and for overlap, I need this equation. That's why I'm not erasing this. So now let's go for SA GO of ligands. So we have 6 ligands, right? So symmetry adapted group orbitals of ligands. So we have 6 ligands, and then we have considered each ligand has 3 orbitals. One is of sigma type, other 2 of pi type, pi and pi prime. So like this. So we have 6 ligands and 2 types. One is sigma type, other is pi. So sigma type is 6 into 6 ligands means 6 into 3, so 80 orbitals. In that 6 are 6 orbitals are sigma type, and 12 are pi type. Okay, pi or pi prime. Okay, because we have considered 6 and then ligands, and then it has 18 orbitals, and there are 2 types. One 6 are sigma type, and 12 are pi type. Now total ligand type is basically sum of sigma plus sigma and pi. Okay, so with this in mind, we can start with sigma. So where shall I write? Okay, so I'm just okay. So with this knowledge, so let's go to the sigma orbitals composition of. So ligands, basically ligands only. Okay. So sigma, you could see it's all directed towards sigma 1, sigma 2, sigma 3, 4, 5, 6, all directed towards the metal. If you consider that, use the projection operation technique. So what you do in like what we did in last class. So we write the reducible representation of sigma. That turns out to be 6, 0, 2, 2, a lot of zeros, 4, 0, 2. You can verify it. Okay, so we can write the reducible representation for sigma orbitals, all the 6 sigma orbitals, and then you find out IR. So IR of sigma, you can say IR. When you find out, it ends up with A1G plus EG plus T1U. Sorry. So I think I'm not doing anything new. So we have octaedral complex. In that, we are following the sigma orbitals of ligands. All the 4 sigma 1, sigma 2, sigma 3, sigma 4, 5, and 6. We are following it, and then we have written the reducible representation. We can say R. Okay, reducible representation, and then you use the reduction method with the Catter table of octaedral complex. Then you will end up with these 3 symmetries. A1G IR, EG, and T1U. Okay, so similarly, you find it out for pi orbitals. So before going pi, I would say we just use only this much. Okay, so after this, what we'll do, we use a precision operator method, right? You can say position method for these orbitals of gamma pi r sigma with six sigmas. When you do that, so A1G, it's very simple. A1G corresponds to what? A1G is basically you will end up with S orbital. So it will have a normalized function. I'm going to write, so it becomes 6. Okay. So I'm not deriving it, but I'm just writing the result. Okay. Once you understand completely, then you can go back and see how we got sigma 5 plus sigma 6. So for A1G symmetry, we get the function. This is S orbital function. You can say just S orbital. This is a function. Earlier we used to write phi, right? Phi 1, phi 2, phi 3. So this is S orbital A1G. So I just write 1 over 6 root 6, and then all this projected out functions, sigma 1, sigma 2, sigma 3, sigma 4, sigma 5, sigma 6. Similarly, one can write for TVU. I rewrite this. So this is done. T1U is, say T1U. Say it's you can see T means a triply degenerate, right? T is a triply degenerate. So it is it will be of Tx sigma x, sigma y, and sigma z. So sigma x, once you get the function, so it will be 1 over root 2. So these are normally constant, and this will be sigma 1 minus sigma 3. And y will be this direction, right? So it's 2 minus 4. And then sigma z is in this direction. So you have 6 or 5 minus 6. Okay, so again it will be 1 over root 2 sigma 5 minus sigma 6. Now you have written for T1U. And EG also you can write. So EG is, you see in that carrot table, EG is, it's a doubly degenerate, right? So you can from the carrot table, EG is what? It was coming as dz square minus y square and dz square, right? For pi or for sigma orbitals, it is sigma x square minus y square. You get one type, and then sigma z square. You get 2 types for sigma orbitals of ligand. So this is x square y square. So it is again 1 over root 2 sigma 1 plus sigma 3.
So last line is not visible.
Sigma 3, sigma 4. So I'm giving the result, okay? I'm not deriving it completely. Again, this one will be 1 over 2 root 3. It's a long one. I think 2 sigma 5 plus 2 sigma 6 minus sigma 1 minus sigma 2 minus sigma 3 minus sigma 4. So this is just sigma orbitals of ligands. We wrote composition of sigma orbitals. In that, we wrote the reducible representation using OH point group, and then by reduction method, we arrive at the irreducible representation A1G, EG, and T1U. So A1G, you always know it is S symmetric. So I'm just writing as a representation. I'm just giving a function of S. That will be normalized function is 1 over root 6, and then sum of all sigma orbitals. This is obtained by precision method, which we did it for last 2 class. How to get the precision? We apply the precision operator to get the symmetry of the orbitals. So these are sigma 1, sigma 2, sigma 3 orbitals. Similarly, T1U is a triply degenerate T1U. So if you see in the carrot table, T1U stands for XYZ. It will be Tx, Ty, Tz. So that means since we are considering sigma orbital, so sigma x, take the sigma x as function, and then you get a sigma 1 minus sigma 3 as the orbital with the normalizing constant 1 over root 2. Similarly, you get for sigma y, sigma 2 minus sigma 4, and sigma z as sigma 5 minus sigma 6, 1 over root 2. Okay, and EZ is left. EZ is doubly degenerate. To see the Gatter table, you will find these two orbitals remaining, x square minus y square and z square. And if you use the precision method, you will end up something like this. Okay, with this, I would say this A1G orbital of sigma overlap with metal A1G. If you remember, I just again going to write the metal orbitals somewhere in this board. So I wrote in the first, right? A1G plus what we wrote, T1U plus T2G plus EG. Okay, so metal, this is metal orbitals we listed in the beginning. So it has also EG orbitals. So EG of this overlap this EG of sigma ligands. So metal EG overlaps with ligands EG orbitals. So they just correlate. Okay, and then T2G. Here we don't have T2G. So T2G we are not writing. Whereas metal has A1G also. So ligand sigma orbital also has A1G. So this one corresponds to metal A1G. They overlap. So metals A1G overlap with sigma orbital of ligand A1G symmetry, and then T1U is there present in metal. So T1U overlaps with T1U of ligands. So T1U of ligand is these three: sigma X, sigma Y, sigma Z. Overlaps with metal T1U. Okay, so in metal, what is so ligand sigma orbitals we have accounted for all three. Okay, but we have considered only sigma orbitals. Now we have to consider the pi orbitals. Pi orbitals, these pi orbitals we have to consider of ligands. We find the same procedure. We write the reducible representation for pi orbitals for ligands, and then we find out IRs. You will find something similar. Once we get that, we apply the projection method, and then we get the orbitals, its functions basically, and then that corresponds to metal T2G. So you can see metal T2G still we are not accounted for. Okay, it is not overlapping with anything. So that will overlap with the pi orbitals of ligands. Okay, so I think I'll continue next class. Okay, I think its time is up. I think. Okay, so I think it's a lengthy procedure. And when you are here, I generally used to take full board to explain much better. We write Gatter table and then draw the structure, and then we completely finish in one board. But in a short space, I'm trying to give more information. But now we just stop it. Okay, what we have done is we have just considered the metal orbitals. We found out the symmetry elements. I mean the IRs which are present, and then ligands, 6 ligands. We have split into 2. One is sigma type, other is pi type. Sigma type we wrote its basis, and then what is surviving we have written, reducible representation we have written, and then we are correlating the symmetry of metal with symmetry of sigma orbitals. So far we have accounted for metals 3 orbitals: A1G, T1U, EG. And what is left is T2G in metal. That will overlap with pi orbitals of ligands, which we'll see in next class. Okay.